This is lecture 1 for week 7 of CS 1030. And in this lecture segment, we're going to pick up right where we left off in the last lectures that you hopefully watched last week. Okay, so let's talk about representing, or talk more about representing numbers using fixed length strings of binary digits. So one thing we can observe is that there's a easy kind of a pattern that binary numbers follow. So if we look at what the values of the bits in the ones place, so that is the the rightmost digit of the binary number, as we count up, that value, the value of that bit is gonna start at 0 and then go to 1. And then the question is, what's going to happen? What's the pattern? Well, it just repeats. It just goes 0, 1, 0, 1, and it does that forever. So if we take a binary number and a large multi-bit binary number and keep increasing up by 1, the value of the bottom bit just goes 0, 1, 0, 1. Okay, so we can basically take the 0, 1 pattern and copy it down to here, and we can keep doing that. We just keep make as many copies as we want. Okay, so that's the ones place, and that's super easy. Okay, so now let's talk about the twos place. So in the twos place, as we start at 0 and keep incrementing a binary number, it's 0 for the first two numbers, and then it's 1 for the next two numbers. So what we can do is we can basically say we take the original set of values from the one column to the right, and for the original set of values, one to the right, we put zeros next to them in the next column to the left, and then next to the copy of the values, we put ones. So the twos place for the first four binary numbers goes 0, 0, 1, 1. Okay, and if we wanted to do that again for the fours place, we would end up with 0, 0, 0, 0 with 4 zeros followed by 4 ones. And this pattern basically where we have blocks of zeros and ones that get twice as big every time we shift one position to the left, that continues, that's a real pattern. It continues for as long as you want it to continue. And so one thing you can do is use this as kind of a quick way to write out the binary representation of a bunch of numbers. So if you want to write out the binary representation for the numbers, 1 through 16 or whatever, or 0 through 15, maybe more likely, you could just use this pattern that I've described on this slide to sort of really quickly write them out. So the way binary digits work is the number of things we can count doubles every time we add a binary digit. So if we have one binary digit, then we can count two things, because the two possible binary numbers that are made up of one binary digit are 0 and 1. So clearly we can only count two things. With two binary digits, we can count four things. With 3, we can count 8. And with 4, we can count 16. And that pattern continues forever. And so what that means is, in the general case, the number of things we can count using a binary number that contains n binary digits is 2 raised to the power of n, or 2 to the n. Okay, so this is really basic and fundamental stuff, and you really need to sort of internalize this and sort of treat this as something that's just understood at all times. Because when we're doing computer programming, we often have to understand this. Okay, so the largest binary number we can represent given n binary digits is 2 to the n minus 1. And the reason it's not 2 to the n is we start counting at 0. So by the time we've counted up 2 to the n times, we've only gotten to 2 to the n minus 1. So if we have three bits in a binary number, we can count 2 to the 3 different things, which is 8. And the numbers go from 0 to 7. So 7, of course, is 2 to the 3rd power minus 1. Okay, and again, just like on a previous slide, this is sort of stuff that might not be all that obvious right now, but this really has to become sort of second nature as you become more and more accomplished as a computer programmer, because this sort of stuff sort of underlies, and we sort of understand this. Programmers sort of understand this at a very deep level, and we just need to sort of start you down the path of thinking about this stuff. Okay, so again, the number of things you can count with an n-digit binary number is 2 raised to the power of n. And the largest value you can represent using a non-negative binary number, and we're going to talk about negative numbers in a later lecture segment this week, is 2 to the n minus 1. So very quickly, if you want to just pause your lecture for a second and figure out how many values 6 bits provide. How many things can we count with 6 bits? Okay, so with 6 bits, we can count 2 to the 6 things, and 2 to the 6 is 64. Because if we take 2 times 2 times 2, times 2 times 2 times 2, we get 64. And so, feel free to work that out for yourself, but hopefully I'm right. And so what we want to start looking at is a question that sort of commonly comes up when programming, which is how many bits do we need to represent some number of things that are out there in the real world? So let's say there are 18 possible things that we need to represent. There's 18 possible maybe colors or person's names or something, and we want to store a binary number that tells us which of those we're representing right now. Okay, so if we want to do that, we basically need enough binary bits in a binary number to enumerate all of the things. So an easy way to do this is just to sort of start counting up powers of 2, and the first one you get to that allows you to enumerate all the things you have is how many bits you need. So if we had 4-bit binary numbers, then we could count 16 different things, and we couldn't possibly count 18 things. It just doesn't work. We can't take a 4-bit binary number and use that to indicate which of 18 different colors we have. It just sort of physically doesn't work. On the other hand, if we had 5-bit binary numbers, that would give 32 possible values, and that would allow us to store 18 different things, or to count 18 different things, and then also there's some left over. And that's a very common pattern in practice. That's how it sort of almost always works. We almost always have some space left over. So the key is to make sure we use enough bits. If we use too many, we just waste a little bit of storage and it's not that big a deal. If we use too few, we can't actually solve the problem. So if we need a binary ID number that indicates which of 8 different items we're doing, how many bits do I need? So if you want to pause your lecture for a second here and figure that out, that would be a good thing to do. Okay, so to enumerate 8 different things, we have 2 times 2 times 2 is 8. So we need 3 bits to count 8 different things. Okay, so now let's talk about something that that's sort of awkward and unpleasant part of programming, which is that sometimes the value we compute using fixed width binary arithmetic doesn't fit in the allowed number of bits for the result. And that's an integer overflow. It happens, a fair bit when in real computer programs. And so let's look at an example of an integer overflow. So let's assume we're doing math using 8-bit integers. And so we have 1 byte of storage. And we want to add the number 255, which is 8 ones, to the number 128, which is a 1 followed by 7 zeros. Okay, so if we do this addition using 8-bit arithmetic, we end up with, the answer is 0 followed by 7 ones, so that's 127, and the extra bit falls off the edge, basically. It gets lost generally, because we're doing fixed width addition, and there is no space for this 9th bit. So that gets lost, and so what happened here is something sort of weird. We added 255 plus 128, and we got 127. So in general, in arithmetic, when we add 2 numbers, the sum shouldn't be smaller than either of the numbers. That's, these are the math rules that we learned in grade school. But it turns out that once we start doing fixed width binary arithmetic, the rules we learned in school don't work anymore. And this is just kind of one of the more unpleasant realities of computer programming. And it's just something we need to kind of come to terms with. So again, there's this sort of unpleasant reality that computers almost always store numbers in a fixed number of bits. So if we had integers, and we're talking again about non-negative integers, stored in 4 bytes, that's 32 bits. So the largest possible number you could store in that is this long number here, which is a little bit above 4 billion. So if you have 32-bit numbers, or if you store integers in 4 bytes, you can count up to about 4 billion things. So that sounds big, right? But you can't count the people on Earth with it. You can't count the atoms in an apple pie with it. You can't count an awful lot of things that actually happen in practice with it. And so these integer overflows actually do happen. Although it turns out that the modern computers, that is to say almost any computer from the last decade or so, including your phone, they almost always represent integers using 8 bytes and not 4 bytes. And so 8 bytes gives you a very, very, very large number. And it is hard to sort of overflow an 8-byte value, even though 4-byte values are sort of relatively easy to overflow using things that you might do. And so one thing you could do on a modern computer is start adding 1 to a counter and see how long it takes to overflow this 4 billion. And it turns out that this happens like in less than a second. Modern computers can add numbers really, really fast. And so anyway, so one of the things that you need to keep in mind here is that as a software developer, you need to sort of understand that these overflows are possible, and you need to take it into account. You need to take these into account when you're writing computer software. And the problem is that software developers often forget about the possibility of these overflows happening, and it ends up being sort of a common source of bugs. And in the rest of this lecture segment, I'm just going to show a few examples. So this is an Ariane 5 rocket that was launched by the French Space Agency in, I believe, 1995. And as you can see in the picture, it exploded shortly after takeoff. And the root cause, so eventually, they did an investigation and found the root cause for this. The root cause was a numeric overflow. There was a value representing the speed of the Ariane 5 rocket that was too large. It overflowed. This caused the computer to get internally inconsistent and confused, and so sort of started a chain of events that led to the rocket being destroyed. And the issue here was actually sort of weird. The software that they used had been written for the Ariane 4, which was a substantially slower and less capable rocket. They reused that software in the Ariane 5, this much more powerful rocket. It just went too fast, and this value for the speed overflowing led to the thing being destroyed, and a satellite was destroyed, and lots of money was lost. Okay, so let's look at a sort of a kind of less tragic example. So I grew up with video games like this, and so you all didn't, but I grew up with Pac-Man, and so the original Pac-Man video game from 1981 or whatever would, after you beat 255 levels, that is, you got to the level 256, would display sort of a bunch of junk on a screen. It was using an 8-bit counter to store something internally. When you overflowed that, it basically just got all confused and failed to show you a real Pac-Man screen any longer. So I'll show one more example, and this one's also from computer games. In the original Civilization game, it turned out that there was it represented world leaders, and the Gandhi leader was given the lowest possible aggression score. So he was given an aggression rating of 1, meaning that he would, rarely, throw nukes at you. So the problem is that there was a condition in the game that would cause aggression of different, that would cause aggression to be reduced by 2. And so what happened is, if you take a binary 1 and you reduce it by 2, and you use fixed length arithmetic, what can happen is it goes from 1 and then it decreases to 0, and then it wraps around to the largest possible value. And they were using an 8-bit counter for aggression, so Gandhi's aggression wrapped around to 255, making him maximally aggressive, and then he would start throwing nukes. Anyway, it's sort of a silly, kind of funny example, but but it shows the kind of thing that can happen when programmers don't understand that integers, the machine integers, don't really follow the rules that we learned in school. And the problem is that they follow the rules we learned in school mostly, but there's these edge cases where they don't follow the rules, and these cause surprises for us.